Okay, let's take a look at our final stress strain problem. And this is one of those classic questions where we punch a hole out of a piece of steel. Now the method that we'll go through here doesn't really matter whether it's a square hole, a rectangular hole, triangular, circular, whatever it may be. The method is the same. The only thing that will change is the actual area of the shear face that will cut out. Okay, so the first thing I notice about this question is that we're mixing units with regards to our dimensions. That is, we're talking about centimeters for the side of the hole, and we're talking about 1 inch thick for the actual steel plate. So with regards to the thickness of the plate, we're talking this bit here, about 1 inch, and the width of the hole is going to be this bit here, which is our 4.2 centimeters. Now we need to convert those into units that we can use more effectively. Now on page 2 of your academic supplement, you'll find that 1 inch is the same as 25.4 millimeters. So we can, if you want, convert the 25.4 millimeters into meters right now, or we can work with it in millimeters. I'm going to choose to work with it in millimeters. So the next one then is our 4.2 centimeters. So I need to go ahead and convert that one into millimeters also. There are 10 millimeters in every centimeter, so therefore 4.2 centimeters is 42 millimeters. So now that I've got my units converted on the dimensions and I'm working all in millimeters, I can now go ahead and start thinking about the question. Well, the first thing I'm thinking about is I'm looking for the load on the punch, and I've been given the stress on the punch. So I'm thinking about a formula of shear stress is equal to the load divided by the area. And I'm thinking, well, if I rearrange that formula to find the load, that would give me my answer. So load would be equal to my shear stress multiplied by my area if we transpose it. Okay then, so the next thing I need to do then is actually work out what that area is going to be, because they gave me the shear stress up here in the question of 162.5 megapascals. What I need to find out is the actual area of my shear face. And when I'm talking about the area of the face, I'm meaning the area of this one, the area of that one, the area of this one that's hidden, and the area of this one that's also hidden on my diagram. Now, if I was to take the hole out of the steel plate and then stretch it out into one long shape, it's going to basically be a great big long rectangle. Now, that rectangle would be broken up then into 4 equal parts, where each one of those parts is 42 millimeters, because don't forget it said the width of the hole was 4.2 centimeters, but if you go all the way around the perimeter of a square, there are 4 sides, and that's where we end up here getting our first side, second side, third side, and fourth side. The other dimension to put on this is the actual width of my hole, or I should say the depth of my hole, and in that regard, that was what we found earlier, which was that 1 inch that we converted to 25.4 millimeters. So if I go ahead and work out the area then, just as a little quick aside down here, the area is going to be equal for a rectangle of length multiplied by the width, where the length going across this way here will be 4 lots of 42. So that's going to be 4 multiplied by 42. And now I can multiply that by the width, and the width, or the depth as I'm looking at it in the question, is 25.4 millimeters. If we multiply all that through, 4 multiplied by 42 multiplied by 25.4 gives me an answer of 4,267.2 millimeters squared. And that's now the area of my shear face if you were to extract the hole from the plate. Well, once we've got the area, I can now look back up to my formula that I transposed, i.e. this one just here, and say that the load that I'm looking for in newtons will be the shear stress multiplied by the area. So let's go ahead and complete that formula. The shear stress was given up here in the question as this 102.5 megapascals. So let's put that in the question. 162.5 megapascals, which means I pick up the 10 to the power of 6. I now need to multiply that by my area. Now my area is down here and it was given in millimeters squared. To put it into the formula, I need to convert it into meters squared. Now as a little quick aside, in case you're not happy doing this, millimeters squared is equal to millimeters multiplied by millimeters. And milli is 10 to the minus 3, which would give us 10 to the minus 3 times 10 to the minus 3. Now, using one of our laws of exponents, where we say that a to the power of m multiplied by a to the power of n, that would give us a to the power of m plus n. And that's basically meaning that if our base is the same, and in our example it is, our base is 10, we can simply, if multiplying the bases, we can just add the indexes. So our index in this example is going to be minus 3 plus minus 3. That's then going to give us a 10 to the minus 6. And that's how we can go from millimeters squared into meters squared. Be careful with this. You do have a little table on page 1 of your supplement that will help you out with this also if you're not too comfortable with the units. So now that we've got that, then back up on my formula, I can say that my area was 4267.2 multiplied by 10 to the minus 6. And that works out nicely because that's then going to cancel out our indexes. So with regards to this then, if we push it through the calculator, 162.5 exponential 6 multiplied by 4267.2 exponential minus 6 gives me a number here of 693.42 kilonewton. And I've just pressed my engineering button on my calculator to express the number in something a little bit more palatable. We should always try and use the engineering button or our multiples or submultiples when appropriate. So in summary then, the way in which we did this, if I just zoom out so you can see the whole thing, is that first of all, we converted our dimensions into metric, in this case millimeters. I then thought about my stress as load over area. I rearranged it for the load, where I then did stress multiplied by the area, and now I had to work out the area. Now this bit here, where we found my area, that's the only part of these type of questions that is going to change. If you were to stretch out, for example, a rectangular hole, it's still going to be a rectangle. If you stretch it out like I did there, just the dimensions will change. If it was a circle and you stretched it out, it would still be a rectangle, and so on and so on and so on. We can then, once we've found our area, dump it back into our load formula and finally work out what the load is required on the punch in newtons. So hopefully this one helps you out, and if you get any of these sort of punched hole shear stress questions, this should certainly point you in the right direction. I'll see you again for another video real soon.